A very good afternoon, distinguished guests and fellow colleagues. My name is Mercy from the Center for Liveable Cities, and welcome to today's CLC lecture series. The center was jointly established by the Ministry of National Development and the Ministry of Environment and Water Resources in 2008 to distill, create, and share knowledge on livable and sustainable cities. So the CLC lecture series, which you are all here today, is really one of the platforms through which urban thought leaders share their knowledge, share their experiences and their ideas, and to exchange best practices in this room right here. So today's lecture is the inaugural session of the Innovation and the City series. This is a new initiative as part of the CLC lecture series aimed to showcase interesting ideas and innovations from both local and international research institutes, thus providing a setting to explore the potential applications of these R&D initiatives. And we are happy to have with us today 3 panelists to share with us innovations of the future. Firstly, Professor George Barbastathis, a Singapore Research Professor of Optics and Professor of Mechanical Engineering at MIT, and he will be discussing today the potential applications for drones. Mr. Michael Budig, Senior Researcher and Module Coordinator at the Singapore-ETH Center for Global Environmental Sustainability, and he will illustrate how robots can achieve otherwise impossible architectural designs. And lastly, Dr. Daniel Gleyzes, Principal Investigator of Vehicle Design and Prototyping at TUM Creates, a joint research program with the Technical University of Munich and Nanyang Technological University. And he will share with us on electromobility and the future of vehicle design. The discussant and moderator of the session is Dr. Johnny Wong, Group Director of Building Research Institute at the Housing and Development Board. Each panelist will be making a 10-minute presentation, starting with Prof. Barbastathis, followed by Mr. Budig, and lastly, Dr. Gleyzes. Before the panel dialogue, we will also have Dr. Wong share with us some applicable R&D initiatives that HDB is working on. The lecture will end with a moderated question and answer session with the audience. And with this, let us start the session by inviting Professor George Barbastathis on stage. Thank you.
So I'd like to start by thanking the CLC for this invitation and this opportunity to discuss a number of interesting topics related to technology and the design of cities. My talk today will be about autonomy, or in other words, about autonomous machines, robots, drones, autonomous vehicles, and so on, and how they can be potentially useful to improve livability and sort of the quality of life in cities, if you wish to wonder what livability is. So I'm a big fan of cities. Actually, I always joke with my friends that I cannot live in a small rural place, so Singapore is a very pleasant place for me because it is quite urban. And but cities are not just for fun. It turns out there's a draw to cities from the outside environment. This is a statistic I pulled up from the World Health Organization website. They say that a staggering number of people, you can see there, about 160,000 per day, they actually move to cities. So as a result of that, the number of people who live in cities in dense urban environments will increase drastically in the next decades. And that creates a lot of opportunities, of course, for growth, industrial and otherwise, that we would not have otherwise, but it also creates a lot of concerns. So I will be telling you today some ideas for how we can create technology to address this issue. So the analogy I would like to bring up is, it's a bit of a cliche, but like every cliche, it has a bit of truth, and that is that a city is like a living organism. What does a living organism require? Well, it requires sensors all of us, we need to see, listen, smell our environment and so on. Then we have a number of actuators, the muscles in our body, which allow us to modify the environment and interactions with fellow peers and other natural objects. And then finally we have a brain. We have a kind of a computer which allows us to coordinate our memories and our current situation and decide how to act accordingly. Most of the time, it does not always succeed, right? But most of the time it does a good job. And on top of that, you have to remember that we have limited resources because we cannot really compute everything. We receive a lot of inputs from our sensors, but we do not perhaps have enough computational power to deal with all of this. So some of our actuations, they happen automatically. Some of those actually, they require the brain to happen. So sometimes you drive home from your office and then you remember nothing about the drive. You did it safely, you followed all the rules, you did not crash into other vehicles, but you remember nothing, right? And that is because it was not sufficiently important to create a level of awareness. Now, on the other hand, if someone cut you off on the way, then you remember that, right? So this is what I'm talking about. Your brain has mechanisms to allocate resources according to the current needs. So it is very similar in the sense that, and of course much more complicated, in the sense that it has sensors that monitor various aspects of what is happening. Some of those are related to traffic, some of those are related to the environment, some of those are related to all kinds of things, water distribution, power, and so on and so forth. And the city planners, they also have ways to intervene with what's happening in the city. For example, a traffic light, in a way, it is an actuator because it tells cars when to stop. The ERP that we have in Singapore is also an actuator because it indirectly controls the traffic by making it pricier in some occasions to drive. And that is one way where you can limit the traffic by making it expensive for people. And in that, as most of you know, Singapore was pioneering, and then other cities, London and so on, adopted it. And in a way, this kind of thing that measures your speed is also an actuator, because if you notice that you're driving faster than the limit, this suggests there's a traffic cop nearby, right? So you better slow down. So there's many ways for city designers to intervene with what's happening. What I would like to address is the issue of how you can make all of these things happen together. And this is, of course, an issue of computation. And in the next few minutes, if you permit me, I will give you a very brief lecture on engineering, a particular engineering approach that is called closed-loop operation. And some of you may use it in everyday life, but I will make it a little bit more specific for you. So in engineering, we always deal with systems. And you can think of your body as a system, you can think of the city as a system, you can think of simpler things like your air conditioner at home, you can also think of it as a system. So what is a system? Well, it is something that requires an input, and then it has a set of rules here, and the output comes out as a result of the transformations that the rules apply on the input. And when you have a system like this, where an input goes in and an output comes out, you call it open loop. And an example is the toaster oven, where what is the input? Well, you turn on the switch, then the toaster oven has a timer, and then finally it says, okay, I'm done. And the same is the traffic lights. They operate on a timer, but they do not have a more intelligent way to interact with the output. So when the toaster oven is done, it has no way to know if the bagel here has been overcooked or if it has not been cooked correctly. It just doesn't know. So this is what we call an open loop system. It is cheap, and in many cases it works, but it is not always producing the desired results. So a better way, I would like to argue, that to design systems is to do what is called a closed loop. And a closed loop system is structured a little bit differently. You do not give it an input per se. You tell the system what you want the output to be. So you want the you want the bagel to be toasted at appropriate level, for example. Or you want the traffic in the city to be at an appropriate level. And anything that deviates from that level, you do not find it acceptable. Now, this is your desired output, which you can sort of think of as the input in this particular system configuration. And then what you do is you actually have another block here that is a sensor. It measures what the output is. And then what you do is you take the actual output of the system, you compare it somehow with the desired output, and then you tell the system how far am I from this desired output. If I am at the desired output, then you don't have to do anything, right? That's very cheap, because then you can coast and you are expending no energy. If you are far from the desired output, then you have to expend some effort in order to get closer. That is the idea of a feedback system. And of course, there's a lot of mathematics and a lot of implementation details that go into it that I will spare you. So I'm not going to show a single equation. I will show you, of course, the air conditioner is a classic example of a feedback system because the air conditioner does measure the temperature. So you set a desired temperature, the air conditioner tries to match it. That's the idea. The ERP is also a feedback system because the ERP sets the price, as far as I know, and perhaps you can correct me if anybody from the LTA is here, but the ERP actually does take the current state of traffic into account. And if it is reaching a level that is perceived as too much, then it will raise the price of the toll, so presumably some people will be discouraged, and therefore you can control traffic this way. So it is a form of feedback. Now, the thing I would like to spend some time discussing more here is the aspect of measurement. As you can imagine, it is critical to take measurements that are, well, they have to meet certain requirements. They have to be comprehensive, they have to be real-time, and they have to be accurate so that you can operate this loop. If you fail to meet those requirements, this thing will not work very well. So, of course, as I mentioned, the city has a lot of conventional sensors, cameras. These are actually speed sensors that people install under the asphalt in the road, buoys that measure quantities related to water, such as, well, they can measure anything, wind, temperature, salinity, and so on. So sometimes these are enough, sometimes they're not enough, and then you have to go and do unconventional sensors. So I will show you examples where your iPhone actually can act as a sensor that can inform the city about what's going on. I will show you examples of sensors that measure quantities related to the water distribution network. We use kayaks, autonomous kayaks, kind of like drones that operate in water in order to measure what's happening in water. And in some cases, okay, we are not really using animals. This is not what I'm trying to imply here. But we can certainly get a lot of inspiration from animals about how they sense things. So some of my colleagues, I will not have time to talk in detail, but it turns out the whiskers of a seal are very clever sensors. So some of my colleagues, actually some of the students are here, they try to emulate, they try to create artificial whiskers that can allow you to sense the environment. Let me show you a few examples. We have a project in my organization at MIT where we have created a fleet of autonomous vehicles that carry sensors. So these vehicles are of various kinds. Some of them are kayaks, so they operate on the surface of the water. Some of them are basically submarines that go underwater, but they still operate completely autonomously. And some of them are flying vehicles. Think of them as like miniature helicopters. Technically, they are what we call quadrotors. And so all of these vehicles, they carry various kinds of sensors. And not only that, but they operate in harmony. They operate in coordination. So they talk to each other by various means. Wi-Fi, well, the vehicle that goes underwater obviously cannot use Wi-Fi, so it uses sonar, it uses, acoustic communication. So they all talk together in order to achieve a certain goal. So I'll show you what we can do as an example with these kind of sensors. So we can address an issue that is very important for the Singapore environment. It is the occurrence of harmful algal blooms that have created major disasters in previous years in fisheries and so on. So it is actually a mystery of how these blooms occur and what is really causing them. And so what we did actually, as it happens, they actually occur at particular times during the year, typically at end of January and also in midsummer. So what we can actually do is we can plan the sorties, the missions of this autonomous fleet. We can plan it to occur with the expected occurrence of algal blooms. And we can detect the bloom very fast because these vehicles, they can carry cameras. If the water develops red patches, then we know that this thing is happening. And these are examples of pictures we took at two separate occasions where the algal bloom was actually just happening, and our vehicles detected it. But remember, this guy is cooperating with the vehicles that are on the surface and underwater. And these guys can measure different qualities about the water. We have sensors that measure temperature, salinity, chlorophyll, all kinds of other things. And then some of our colleagues at the National University of Singapore, they actually put together all of this in a model that also takes into account weather and other environmental conditions, trying to predict. And I'm not going to tell you that we have solved it yet, but we're making very rapid progress, because for the first time ever, anywhere in the world, we actually have real data that correlate physical quantities about the environment with the actual occurrence of this very destructive phenomenon. So this is an example of what unconventional sensors can do. Another thing we do is we have sensors that can measure particle or bubble concentrations in water. So I will not tell you details. This actually happens to be my own specific area of expertise, where we capture images like this on the camera. This is now a standard camera, but what we do is some signal processing that allows us to recreate in 3 dimensions the positions and sizes of these bubbles. And these are very important. Again, I will spare you some of the details, but some of our colleagues who understand fluid mechanics, they can put this data in their model, and then they can create useful predictions related to oil spills, land reclamation, safety, and so on and so forth. So, for example, we can help some of these scientists determine what is a proper way to deal with an oil spill. Some of you who maybe have been following this literature, there is a controversy now. If an oil spill does happen, should you try to contain it by confining it with a boom, or should you do the opposite, which is to use a surfactant to disperse it and then hope that the various organisms in the sea will actually eat? If you can believe they can do it, they can actually eat the gasoline that has leaked. So it is actually not clear to the scientists what is the best way to approach the problem, but by creating this sort of very rich data, we can help them address the issue. I will show you 2 more examples, and then I will conclude so my colleagues can take their turn. One of them is using smartphones as a way to measure traffic in the city. So your smartphone contains, for example, it can communicate by Wi-Fi with other smartphones, and when you do that, you can create patterns of concentration of people at bus stops, at buses, at various other places in the city. Then you can create patterns of activity in the city, and then you can use them in the feedback loop I was presenting before, for example, to adjust the patterns of transportations. You can control the traffic lights this way, you can control where the buses go, and so on. I'm not saying this is happening, but I'm saying that some of these technologies can enable it, and it might indeed happen in the next few years. And of course, once you can do that, then you can decide how you can actually adapt. For example, you can decide how quickly you can adapt the route or the schedule of a particular transportation mode. For example, if you want to change the route of a train, it is not a very easy thing to do. It costs you billions of dollars and years to build a new train line. But on the other hand, because the trains operate on tracks, they're not affected by traffic. So it is actually quite easy to send trains in a particular hotspot, provided you do not crash into other trains. Okay, in places like Tokyo, there's express tracks that the trains can actually go very fast. We do not have those in Singapore, but we can still manage quite a bit, even with this limitation. Then buses, of course, are kind of the opposite. It costs nothing to reroute a bus, provided you can inform the customers so they don't get surprised by the new route. But of course, the bus is subject to traffic, so it can get stuck, right? Unlike the train. And then finally, many of my colleagues and one of the following speakers will actually talk about autonomous cars. This is a very big deal in Singapore and elsewhere in the world. And it is not my expertise, so I will leave it to my colleagues to tell you more. But it is a very interesting way to deal with it, because you can deploy autonomous cars on demand if you have them. And also, even though they're subject to traffic, they can be programmed very efficiently, so they can actually avoid the traffic hotspots, and instead of making traffic worse, they can actually alleviate the traffic problem. This is the promise of autonomous vehicles. And the last thing I want to tell you is a topic very, very dear to Singapore, because water is a very scarce resource and extremely obviously crucial for Singapore as a nation, and that has to do with monitoring the state of the water network. I'm already over time, so I don't want to abuse my stage privilege here. I will just tell you that some of my colleagues, they've developed a network of sensors, and they've deployed it in the pipes of the water distribution, and then based on that they can monitor the water flow. They can also predict events such as bursts, or either they can predict them or they can detect them very quickly after they happen. And based on that, of course, they can deploy either crews to fix the problem, or in a more automated fashion they can adjust the water flow in order to cope with a particular situation, whether it is increased demand due to F1 traffic or what have you. And these guys, they've actually started a company that is commercially deploying this technology now in Singapore, and it is the company is Singapore based, and they will deploy the technology in Singapore first, but obviously possibilities out Singapore also exist. So finally, what I would like to say is that feedback is a very interesting and promising way to run the city, and I would like to suggest that it is a very productive way to plan for the future of Singapore in the next decades to come. So maybe I will stop here and pass the podium to the next speaker. Thank you.
Thank you from my side as well for the invitation. Thank you to CLC. I will talk about innovation in the city from a designer's perspective. I'm an architect by training, and so are all our team members actually. And I will talk about our project here in Singapore, which has the title Design of Robotic Fabricated High-Rises. So I will give you just a very brief insight into the background, and then at the end I will show you 3 projects that we are currently working on. Our team is embedded into the Future Cities Laboratory. The Future Cities Laboratory is the first project run by the Singapore-ETH Center. The ETH is a Swiss university from Zurich. And this university, the Swiss Federal Institute of Technology, together with the National Research Foundation in Singapore, funds this project. Our work is embedded in a quite large field of research. So when we talk about Future Cities Laboratory, we talk in fact about 13 different groups, and I'm representing one of them. So when we look at cities, we look at 3 different scales. We look from a very large perspective, which deals with territorial organization, landscape ecology, and also mobility and transport. On the medium scale, we would talk about urban sociology, about architecture and urban planning. And on the small scale, we will still dealing with what for me is a large scale. We will talk about, or we're dealing with low exergy, with dealing with energy design, architecture and construction, and coming to our project is digital fabrication and architecture. So our team here in Singapore consists of 6 permanent researchers and 2 principal investigators coming in and out. And we do research on PhD level, and also we work with master students in architecture in a design studio. So what are we challenging? We're challenging 2 main topics. One is we're challenging the typology of high-rises. We use the architectural typology of a high-rise as a test case for our research. For several reasons. One, it's a very apparent typology in Southeast Asia. Singapore, for example, is ranked number 4 worldwide in number of high-rises. And what cities usually communicate is a picture like what you see right now on the screen is it's a picture of diversity and which it designs. What we also want to challenge, though, is the construction paradigms which are behind these typologies. Again, in Singapore, 90% of the population is living and working in high-rises, and the reality, if you look at the back, at cities from the backside, the reality is very much different from what is communicated. Its variety is a bit more limited due to several reasons, of course, and one of the reasons is that the current construction paradigms in the building industries are still very much rooted in an industrial age. So the invention of the fabrication plant, or also inventions of the invention of the high-rise, that's almost 150 years back, and the whole industry, like opposed to, for example, the car industry, the construction industry has not changed very much, really. There were several attempts. Again, on the left side, you see how the car production industry has improved. On the right side, you see examples from Japan from the 90s, where there were several attempts of automation in the building industry, but they were not really successful. The speed was a little bit, it increased compared to conventional construction methods, but it was still very much the same if you compare it to the effort which ran into the whole thing. And one of the most apparent issues was that these attempts were very much trying to bring the concept from other production industries into the building, meaning they were creating a closed environment, which you see on the very right side, to kind of shelter this whole construction progress. And that made it very unflexible. So you could only produce one very specific typology with one kind of large machinery. There are actually two examples here in Singapore. One is the HDB hub in Toa Payoh, as far as I know, which was constructed with such a typology, with such a technology. So what we're looking at different construction machines. Again, on the left side, you see a conventional construction machine. It's lifting very large and heavy pieces. On the right side is somehow an illustration of what we try to perceive for the future of construction. Now, about 7 to 8 years ago, our team has implemented this robotic arm into an architectural laboratory. And it was by doing that, it was actually the first team worldwide to start looking at robotic technologies and how to make use of them in an architectural and designer environment. What it really means for us is the following thing. If you think about how buildings are constructed, we like to take the brick wall as one of the examples for several reasons. One is that the brick is one of the oldest building components that is available, and another reason is for how you can handle it. You can handle it manually, but you can also test how to handle it with a robot. So on the left side, you see a student several years ago trying to figure out what possible configurations you could build with bricks, actually. And now, in order to control a robot, of course, you need to translate this logic into a code, into a little programming code, and then you can program the robot. And the interesting thing about the robot is when you look at this brick wall as one of the key examples, every one of us is able to imagine how a normal brick wall looks like. And you could probably imagine as well that it's possible to build something like this by hand. But if you think about what it implies, you start realizing how difficult it really would be, and that it would not be feasible at all. The robot, on the other hand, does not really mind to do the same procedure repetitively over, but it can actually change that like from step to step, and that's why you can position each brick in slightly different rotations. This kind of logic was applied to different material concepts, not only bricks but also wood construction. There were several attempts in concrete, with plastic material, all on the one-to-one scale, as you can see here, like ranging from like a 100-meter long wall, which was installed at the Venice Architecture Biennale in 2008. Then you see in the middle, you see a facade for a winery in Switzerland, and on the right side you see a project which is currently built. It's a 2,000 square meter roof out of wood slabs for a new building at the ETH campus. So again, one of the attempts that we're looking at is not looking at smart and not looking at large and unflexible machines, but at small machines which can be applied in a smarter way and which are much more flexible. Why we do that? Because we believe that still loads of resources in the building industries are wasted. So one of the potential advantages are, if you look at the right side, you might notice in the diagram that walls are much thicker in the bottom than they are in the top. So the current construction paradigm forces us to make the same wall, no matter if it's at the bottom or the top, because it's just cheaper to produce it in the same way and then to vary it. And of course, as I mentioned at the beginning, I'm looking at it from a designer's perspective, so I'm also interested in what implications this could have on future design. So to conclude, as I said, I would want to show 3 research projects that we are currently working on. This is our research laboratory here in Singapore. We are based on NES campus in the Create Tower, and we're working with these 3 robots which allow us to do to work on scaled models, and it also allows us to look at one-to-one applications, so small one-to-one applications. One of them is a very short-term research project that we're currently working on. It deals with the process of tiling. Tiling is very labor-intensive, and we after like several conversations with Singapore agencies, we identified this as one potential application which should be able to be done in a rather short-term period. So again, we try to bring in a small machine which is able to actually go into rooms and lay tiles. And just to give you an idea how it actually looks like working with robots. You see this movie where the robot does not only apply the mortar on the floor, but then after this process, it's also applying the tiles like piece by piece. So this whole project has only started like 3 months ago, so it's in a very early and still very immature stage, but it's very promising, as I said, because it can be applied in a very short-term range, ranging between 1 or 2 years. So here you see how a researcher is feeding the robot with the tiles, and the tile is grabbing them and placing them. And right now we're also dealing with implementing sensors into this kind of process in order to make it more precise and with less deviations. The second project that I would like to highlight is called Mesh Mold Formwork. This is more long-term research. So we've all been confronted recently with this hype about 3D printing technologies, and of course this promises to be a very potential technology for many industries, but it's questionable how it can be applied to architecture. But nevertheless, we were curious about it, and we dismantled a 3D printer and used it actually in a way to extrude plastic material in space. It's not a brand new concept, but in the way we applied it, it is new. Nobody has thought about it in that way. So we can create these 3D meshes which can become the size of a wall. And what does this mean now? This is not the wall itself, of course, but there is a technology called leaking formwork. So you can build these formwork systems, these perforated formwork systems out of plastic, and then pour not so liquid concrete into it. It protrudes the surface, and then you can trowel it, and you have a perfect concrete wall. So this is a very interesting concept that we apply here. And what we do here is we use one of the potential of the robot to move without any constraints in space. And we don't do it by moving large pieces, because this would be difficult by robots, but we do it by small pieces that actually inform the concrete. Since concrete has this liquid state, it can be formed in almost any shapes, but it would be very difficult to do because you need a lot of effort to be done, to be gone into the formwork. So here you see the formwork, you see the reinforcement which is inside, and we are now trying to fold this into one process by making this formwork built by the robot, and by also activating it as the reinforcement. So here you see a small 1:5 scale example. This is so the first proof of concept that it can work, and how it can actually work. And then as a last project, I would like to just give you a very brief insight into the methodology behind. So it's not about only about applying the technologies, but it's also about how we change our way of working with these machines. So here we work with more than 20 master students from ETH Zurich and from NUS Singapore together. And in this studio, which is called Design of Fabricated High-Rises, we ask our students to build 1 to 50 scaled models. So a 1 to 50 scaled model of a high-rise quickly becomes more than 2 meters high, almost in some cases up to 4 meters high. And the interesting thing about it is, if you ask students, or if you ask designers to build themselves while they're designing, this process becomes synchronized. So designing and building is synchronized. You could never design something that is not buildable, since you're in charge of it, and since you're yourself responsible for it. And you just get a hint on the screen how this environment changes, like what our interfaces look like, and that we're actually dealing with building our own tools. And I would like to conclude with this slide. Of course, we know the towers that our students build are abstractions. They're 1 to 50 abstractions of a reality. But we believe that this different approach and this different methodology will actually, on a long-term basis, also have effects on how we work and how we produce architecture and building environments. Thank you very much.
So ladies and gentlemen, also hello from my side. I would like to present you today the work of TUM-Create regarding electric cars, electric vehicles. And first I would like to tell you what is TUM-Create at all. So TUM-Create, as already mentioned before, is a joint research program between the Technische Universität München in Germany and the NTU here in Singapore. And we try to target all key issues regarding electric car, electric mobility, how we call it, and specifically for tropical megacities. We are funded by NRF, and right now we are 125 researchers, mainly from Germany still, but we have already quite good share also from Singapore and all over the world. Specifically, we have 10 focus groups or research groups. They are grouped in 4 clusters again. On the left side you see the group which is dealing with everything that's regarding battery, starting from battery chemistry, so really molecules, forming new molecules for new batteries, going up to battery cells to understand their behavior, and going up to really system-wise to battery systems. In the second column, it's more or less all topics about ICT, and the third column is about electric cars with a special focus on air conditioning. And the fourth big group is about larger scale, so transportation and also how does energy come actually to your vehicle at the end of the day. So it's energy management, or how we call it infrastructure. I represent those two groups, vehicle concepts and vehicle prototypes. I will show you a little bit more what we do here. In general, people will ask, okay, why electric cars? Is it a hype, or is it sustainability? We believe, yes, on long term it will be a solution for the future, mainly for cities, for mega cities. There are a lot of reasons. I don't want to go through this, but it makes sense on the long term. It's questionable if it will have success in the next 5 years, next 2 years, but long term we are pretty convinced it will be. At TomCreate we have in the last 2 years finished, or we are partially still in the process, done 3 vehicle projects. From the left to the right you see projects which are showing the readiness for the market. On the very left side, where we think it could be ready in 2 years, and the one I will explain to you also later, which we see more in 20, 30 years, so really a research project. Let's start about VOI, which stands for elephant, by the way, in Vietnamese. Safe, not heavy, safe transporting. It's thought as a scooter for traffic congested megacities. So in fact, actually not for Singapore, for more developing megacities like Bangkok, Jakarta. Imagine the following situation. You have a lot of traffic jam, but at the same time you would like to go very fast from A to B. So more or less you have 2 options if you don't have a helicopter. Either take a car, that be a taxi or a private car, or you take a scooter, but you also see here. Both have their advantages and disadvantages. A car is safe, comfortable, but you easily get stuck in the traffic. A two-wheeler again is quite fast, it can weave through the traffic, but it's not comfortable, it's not safe, and also not protected for weather. So we thought, okay, can we combine the 2 advantages and leave out the disadvantages? And we came up with a concept actually originating from a priest in Germany. So no engineer, no designer, it's a priest, and he approached us and thought, okay, let's think if we can do it in reality. The idea is here we have a passenger in a safe capsule in the front where he has a good view, and the driver is in the rear. As we not only want to do something in virtual reality, we also have proven that this is actually doable. A team of 6 master and bachelor students, both shared from Singapore and Germany, have done this in a time of not even 7 months. And I only have a fraction of the video because of limited time, but as you can see, it's really working. It's a very first prototype, so there's definitely still a way to improvement. We still have not implemented air conditioning in this. That's the second stage we want to achieve. So yeah, the guys have really fun. I was already asked it before. We actually had an offer by an investor to bring this actually really to the market. However, it means really to really go into a production liability issues, etc. Where I think we at TomCreate would not be able to. So in fact, we would also need really engineering effort, engineering companies, not only investors, to go the next step. The second vehicle, by far the largest project we are running here, we're having roughly 30 PhD students and young professionals in this, plus again roughly 30 master, bachelor and interns on this project. It's called EVA. It's not standing for anything, it's just called EVA. And this is a taxi for Singapore. So our target was here somehow also to showcase something really realistic and maybe with 5 years lead time for serious production to achieve something that's also valuable for Singapore. So why taxi I can maybe explain also later on, but I think the main argument is really it's having a very strong leverage effect. Taxis only amount for not even 3% of the vehicles in Singapore, but in the same time for more than 15% of the mileage. So exchanging every diesel and natural gas driven car to electric, you could reduce dramatically local and also global emissions. The main feature, so what can you actually do as a research entity to make something better than an OEM? We want to set here a benchmark regarding comfortability or market readiness regarding range and charging time. Price is another issue which we don't tackle here directly, but this car is thought to have a range of 200 km realistic driving, so means not a driving cycle, but realistic driving, here based on Singapore, traffic plus air conditioning switched on, plus all auxiliary systems. And at the same time, we want to recharge this distance within 50 minutes. So wherever you look, it will not be existing somewhere in the world. We are also aware that we are still in research phase. It's no serious car, you cannot purchase this, but we try to make it as good as possible that within a second phase of 5 years, which is common for automotive engineering, we think it could be placed on the road. We have some more, let's say, more taxi specific issues, like I'm being a young father, I want to do something for protecting also the children, and we have in a research project with a few students also an integrated child seat. As you can see here, it's integrated in the front seat, which is foldable, and then flipping out a small protection layer for a child. It's a minimal project, but we also try to come up with a solution where we reduce actually the energy consumption and at the same time to increase the comfort. Mainly in thermal ways, you can really do a lot. Just a number, roughly, air conditioning takes about 700, 800 thermal watt away constantly if you're driving here. This number, maybe nobody knows, is quite high if you compare to driving. If you drive a car, it's about only 3 kilowatt average here in Singapore, roughly 3-4 kilowatt in average. So it's a very high portion. To reduce this thermal takeaway from air conditioning can have a big leverage again. So what we target here is a more ergonomic approach, to have your head as the most sensitive area of the body. We try to cool mainly this one, not overcool it, but therefore we can leave the all-over temperature of the cabin at a higher temperature. And again, we can reduce the overall energy. I wish this whole lecture would have been 1 month in advance, or roughly in 1 month, because we are going to Tokyo Motor Show to present this vehicle, and I cannot show you the actual design right now because we will reveal it only then. But I would like to show you some work in progress and just show you this car is meant to drive actually. This is some very cooperative colleagues from Admiralty. With the very first part we achieved, this is so-called main tub, where everything else is placed on. Later on to the right you saw a lot of more parts made of carbon fiber reinforced polymers. And at our second big collaborator, Hope Technic, I saw here one colleague of Hope Technic, building up the whole body here in carbon fiber. This is, as far as we know, the biggest or the largest carbon monocoque in the world that is here built up. This is staged roughly 2 months ago, I think, where we had the first marriage of the body and the drive structure, so the exhaust system. And the last image, that is still not showing the design, but roughly where it's about 1 month ago, we are implementing now all the drivetrain systems. In not even 2 weeks, the vehicle will be flown to Tokyo for presenting the vehicle there. So our target is to finish the car fully. Of course, we have to. And well, it is a really good surprise. We can even drive it before and show actually that it's working. But the actual target is to the very first test drives to do it in early 2014. But yeah, the big event will be just in not even 1 month from now on to showcase actually the ability to do this here in Singapore. This is for me, coming from BMW, unique. We have done everything here in Singapore, 100%. Idea, design, development, production, assembly, everything you can think about, and this is the very first time this has been done here. I will come to the next project very quickly. This is something where we think it's very far in the future, where we had 4 master students think about, you have all freedom of your brain, just take away a lot of boundary conditions which are existing right now, think about what you think the future would be like. So what they came up with is called Gemini, a future mobility concept. This is something not very new. It's a detachable car structure thought to have really reducing the traffic on the road. If this one is only 1 meter long, still safe, you can save a lot of traffic again. At the same time, if you want to go on higher speeds, you would have to have more stability and you would have to connect them both together. We looked with one person for 1 year also in the technology. It's not possible to do it right now. pneumatic-wise, electric-wise, even mechanical-wise, it would not be automatically possible right now. I will just show you some artist impression, how it can look like. Maybe you see where it is thought about. Maybe in 20 years we can think about something like that, looking very futuristic, very nice. They even have some, I think, Singaporean names. And I would like to conclude with this, let's say very far and not the most realistic view to the future, my presentation here. So thank you for your attention.
Okay. Very good afternoon. My name is Johnny. I'm from the Housing and Development Board. I'm actually the moderator today. So when CLC first invited me, I thought it was an easy job. Then after they called me and says that maybe it's good that I present something to share with everybody what HDB does in terms of our research area. And it might also present a very good discussion base with the three speakers, as maybe give them a better understanding on what are things we're looking at in terms of research, and maybe they can suggest ideas that how they can actually work with us if possible. Okay, I think for those Singaporeans and even some of our international friends, you would know that the story of HDB. We were set up in 1960s. That time, most of the focus is housing the nation. So it's really moving people from the slums into very basic housing. But over the years, we have tried our best to improve the quality of our buildings and also the estates. And in recent years, we are pushing for more sustainability, improving further the enhancement of the livability, and especially now with the so much ICT development, we're also trying to see whether can we drive for more smartness in our towns. So we are housing something slightly more than 1 million. We have more than 1 million dwelling units now, and you appreciate that having so much developments on the ground and also managing some of this. To meet these challenges, we actually have a roadmap drawn up to ensure that we continue to deliver better living for the HDB towns. We are guided by these three trusts. We strongly believe that our towns should continue to be well designed, well planned, and of course must have a strong focus on sustainability and livability. And of course, while these are the hardware, the soft aspect of it, that means a community-centric town, is also important, and how can we continue to drive this? So with that, 3 years ago, the board felt the importance of setting up a formal research institute, and that's where I come from, the Building Research Institute, or BRI for short. We had a very ambitious vision, and that is to be the leader in housing research, innovation, and solutions for driving a sustainable living environment. And I thought this picture shows very well on how we actually drive research over at HDB. Basically, we want to work very closely with the research institutes from other places, whether it's private companies or even the academics, basic research or even applied research. And then we explore possibilities to enhance our buildings and estates, or even look at how to solve some of the problems that we're facing on the ground. So when this new concept comes out, we will produce prototypes, and these prototypes will be tested in our master lab. Master lab is located in Woodlands. It's the Center of Building Research. Show you a bit of that later, where we conduct all these ideas in lab conditions to make sure that we ensure the functionality before we identify for adoption, and that would be where the pilot test and the test bedding takes place. And most of this will actually be taken place in what we like to call nowadays as the live-in labs. We have identified precincts or even the whole town as some of our live-in labs. Again, I'll share with you. I mean, Pongo is actually one of our live-in labs. And if successful, and most important, why we need tests in live-in lab is whether the residents accept it, and long-term, the sustainability of it. And we'll roll out in a wider scale. And with the economy scale, we hope to press the price down, the cost, so that not only HDB, but hopefully the private also get to enjoy some of this. And of course, we are quite ready to share with the local industry and global industry what the learning experience we gain. So this sums up, and I think like most research institute, we cannot do everything, so we try to focus on some key clusters that we do. And some of them includes like these 5 clusters essentially we drive. Energy, very important, urban greenery, waste and water, living environment, and of course building technology. I go through very quickly because I'm actually just a moderator. I'm not going to give you a full lecture, but in energy, we have a 2-pronged approach towards reducing energy consumption in our estates. The first thing is, of course, try to reduce the energy usage. Very easy, and that is through energy efficient, through technologies to drive this down. And whatever that the energy needed, we see if we can use clean, renewable energy. So we also test bed on solar. For solar, our experience with solar has been quite long. The cost was very high. The knowledge of it is also not so sure during the time when we first started. But I'm happy to say that we have pushed on, and recently we have seen that the price of solar has dropped, and we are actually implementing in a very large scale in our housing estates. Another one that we tested on energy efficiency, if I may, just very quickly, is this what we call as regen leaves. This regen leaves is based on the motion of the leaves. We are able to actually capture some of this energy and then use them. So it helps to reduce the energy consumption of leaves for about 20%. And this is also wide-scale implemented in some of our towns. For urban greenery, I think it brings down ambient temperature, aesthetic, so that's important. Some of the things we are testing out is vertical greening and rooftop greening. Well, this seems simple because most of the other countries, like especially in Germany and Japan, some of this technology are already very well established. We took some time down here because we were a little bit careful. A few challenges presented to us. First, of course, is cost. The other one is that the species must thrive well in our local context. So we actually spend a lot of time testing the species to make sure that they have certain properties like regenerative and what have you. But most important thing is that the maintenance is low, because otherwise, while we introduce all this, if it costs too much for our town councils to maintain it, we get a problem when they started considering increasing the SNCC charges. So these are the things that challenges presented to us. In recent years, we are now looking at biophilic towns, how to actually bring some of this greenery and associate to the living conditions and the health aspect of our residents. Okay, and we also have our landscape guide that we help to work with the consultants and share with them our experience. The other one is water and waste. Just some very quick snapshots of what we are doing. Of course, the water-sensitive urban design. We are doing some testing together with PUB. Rainwater harvesting. This we started back in the 1980s, but it didn't work out well because the water was not used as what we hoped for, and they become stagnant water, algae growth, and mosquito breeding. But we have improved that over the years with different types of technology. Now we're using membrane technology. The only problem with rainwater harvesting is always cost. So, but that didn't stop us. Now what we are doing is that I think this flooding mitigation measures, we are trying to combine the two together, and then we see whether is there opportunities to reduce the cost because it serves two functions. The other one we are looking at is centralized chute for recyclables. I think that one, while it's been announced in the papers and everything, it took us a lot of time studying just the right design to put in our buildings. Now we are going in a big way is this pneumatic refuse collection system, district level. We find great opportunities here because that will actually increase the productivity of the collection process. Imagine the truck, instead of going to every blocks now, just goes to one of it, which has all been sucked. into a central bin and just collect from there. The other one, that living environment, we are looking at all the advancement in modeling tools to see how can we use it to our advantage to model. We started with units, then after that with a whole building, and now with a whole town. The town that you see in this animation, let me see if I can get it, it's actually Punggol. We modeled for the whole Punggol, and that actually allows us, not only at precinct level, but also at whole town level, how we can ensure that the wind still actually goes to especially those existing estates, which is at central of Punggol. So this presents quite a good for our good information. Okay, so wind map is something that we have built, and we are looking at our towns. We are also doing shadow analysis, solar irradiance, thermal comfort mapping, and noise. But in recent time, we are also looking at complex systems to see how can we actually combine all these things and also justify some of the urban solutions that we're going to bring in. So that is something hopefully I can share with some other time. Building technology, I think precast, that's something that we are good at. I think with the advancement in robotics, maybe there are opportunities to expand from it. Okay, so I won't go too deep into it. Just now I mentioned we do have a master lab for our R&D, and that's at Woodlands Center of Building Research, where we do most of our testing here. We set up live testing for most of the things that we are driving. And then the integrated living labs, currently now we have two. The one of it is at Punggol. Punggol is for all the new developments. So these are some of the things that we test bit down there, and then we replicate it. The other one, which we find that our existing estate is important. And HDB owns so much of the estate. So we are actually starting out a green print at Yuhua. This is an existing estate now. The challenge in bringing technology to existing estate is that you must work with the community to make it work. Okay. I think this is going to be my last slide. Just say that moving forward, there's a lot of opportunities. So we want to continue to work with our partners to see how can we actually drive more livability and sustainability in our towns. Okay, that's all. Thank you.
Thank you very much, Professor Barbastathis, Mr. Michael Budig, Dr. Daniel Gleyzes, and Dr. Johnny Wong for their very interesting and insightful presentations. And I'm sure their presentations have probably given our audience here some food for thought on the innovative designs and the future for drones, for robotics building, for the future of vehicle design, and of course our sustainable public housing developments. So right now, may I now invite our panelists to come on stage to have the panel dialogue session with Dr. Johnny Wong. I will now hand the time over to Dr. Wong and the panelists. Dr. Wong, please.
Thank you. Okay, well, I've just presented what we do in HDB. So first of all, I'd just like to thank the three speakers. I think I found the presentation very interesting. And actually, some of them I already know because I think we've been working very closely with some of your research institutes. Maybe as a first question I thought I'd pose to each one of you all is that you've seen what HDB is trying to drive. And I can see great opportunities in the three areas that you're looking at. Maybe at the start, I can invite you all to give some views on possible ideas that you can give us, perhaps HDB or even other agencies that you see that areas that we can, that you're looking into that we can consider some ideas. And if you may, I'm sure you also thought of what are the challenges that you actually face if you were to introduce in Singapore. And those are the areas that probably research can help or even looking into. Maybe I invite George.
Okay, thank you. Yeah, thank you for letting us know what is happening at HDB Research. I think it's very exciting work. And I think there's a lot of opportunities for integrating some of our work. Speaking from my point of view, obviously very interested in adaptive technologies. And it's kind of difficult to imagine a housing estate being adaptive I mean, after all, once you build the walls, it's there. But there's other ways that you can make it adaptive. For example, with some of the technologies that my colleagues presented, both in terms of using robots to change the way you build, but perhaps this can be combined with the sensors that allow you to notice in real time what is happening in the estate. For example, a large concentration of people may need more air conditioning, and then adaptive reallocation of resources, and then also combining it with transportation. After all, the location of your house determines globally what happens in the city, because you have to go to work, you have to go to shopping, and so on. So I think there's many opportunities for closing this feedback loop, where the estate is actually responsive to the needs of the residents and tries to adapt its operation to meet them in the best way.
Maybe I mean, instead of just going down, maybe I just add that actually smart city is something that HDB is also looking into. But we do face some challenges. Maybe I can tap your expertise in this area. One thing is that I think earlier before the lecture, I was also sharing with you is that, well, we want to put sensors so as to help. We see value in it. First in estate management, and also knowing the behavior of some of our residents, so that maybe we can plan our towns better. But the challenge we face is that the deployment of the sensors is one, so that they actually make real value for us, rather than just place them all over. That's one. The second thing is that we also thinking in terms of the legal implication, because while we are doing it, so we think, for the better good, to people it may be intruding some sort of privacy, you know. So maybe something you can share.
Yeah, sure. Let me address the first topic, because it is a little bit easier. So sensor allocation, it is a very interesting problem in optimization theory, and this is not my expertise, but I know a lot of work has been done on how you can, if you have a limited number of resources, as you always do, which you can translate typically in dollars or number of sensors and so on, then depending on the situation, you can optimize their locations. And thanks to some of these technologies I was discussing, such as drones or autonomous vehicles, you can also consider changing the sensor locations in response to a situation. My favorite example is F1 events. In F1 events, you have huge crowds of people gathering in certain areas of the cities, and then it is important to allocate the resources in a way that you know precisely what is going on, to deal with emergencies, heart attacks, potential threats, and so on and so forth. So it's very important to know how to move the sensors. And some of these autonomous technologies, they allow you to do it in a cheaper, smarter, more efficient way than actually having people carry cameras or what have you. Now, the second topic is, of course, a very sensitive one. There's two ways to go around it. One is to simply use existing sensors. I mean, everybody knows that there is security cameras in many places. These are already there, and I presume they have been placed in a way that already is legal, so it addresses any legal concerns. Similarly, there's other sensors that we have that measure temperature or other environmental qualities, and there is also creative ways that some of my colleagues at the Smart Center are exploring, where you can actually use everyday devices. You can make legal use of them as sensors with user consent. So an example that is my favorite, and I do not have time to present, but maybe I can take the opportunity now, is how you can use your cell phone, your own cell phone, as a sensor. So my colleagues, they actually have a project together with the LTA, where they have people, residents of Singapore, they sign up as volunteers in a program that allows them to use their phone as a tracker of their transportation habits. So at the moment, actually the LTA has been doing these surveys for a long time. They simply distribute forms to perhaps 1,000 people, and they ask those people to every day to fill out a log of what they did. For example, I used the bus to go to work, and I used the MRT to go to Orchard Road and so on. And of course the form, they have to fill it out every day, so it is kind of onerous, and also it can be inaccurate because sometimes you forget what you did and so on. So what my colleagues did is they actually created an app that I believe you can only use on an iPhone, but maybe there's an Android version too. And you sign up voluntarily, right? So it is with your consent. And then once you sign up, then your phone has various ways of measuring where you are and what you're doing. For example, your phone has a vibration sensor. This is how you know, when you rotate your phone, it adjusts the screen, right? If it is vertical or horizontal. Well, it turns out this same sensor can be used in order to measure if you are in a car or a bus or a train or if you're walking, because in each one of these 4 scenarios, there's different vibration patterns. So my colleagues, they actually worked out how you can use your phone with basically at no cost at all, just the simple act of downloading an app. And you can then, as a planner, if you're the LTA or a researcher, you can derive a lot of interesting data that you can then use for your planning. So this is an example where you can get creative, you can do it completely legally and with full user consent. And after all, the user has the capability to turn it off. If for whatever reason they don't want to log some particular activity, they can turn it off. So I think this is a very good way to address privacy concerns, and I think you can generalize these approaches in other examples. So yeah, I hope that answers.
Yeah, thank you so much. Maybe we move to this, Michael, and we can share some thoughts on like what I've asked earlier. How you think that what you're doing now can actually be something that whether it's HDB or even BCA can think about.
I would just like to follow up briefly on the sensor technology,
Sure,
but
sure.
leading to that, it's interesting because looking at technologies, we're also fascinated by what how sensors could improve what we're dealing with and how to deal with adaptability. And it's a very tempting topic in architecture as well, but in the end we're still working with a static environment because it needs to be built at a certain point, and once it's built, it's not so easily adaptable, unfortunately. I mean, there were attempts in the 60s and 70s where they tried to build up on a modular basis. What we're interested in is creating environments which are adaptable, but in their inherent matter. So when I'm talking, this is now where I'm coming to HDB, where my interest lies in. When it comes to design, this is a very important issue to me. And if you talk to the public, usually design is only considered to be to make facades look a little bit nicer, but that's not what we consider as design. When we talk about design, we make things more meaningful, and we implement more functionality into them. So if you look at a facade, for example, if we use robots and if we use their potential to make more variation, to build differentiated facades, we are talking about each flat, for example, has a different position towards solar radiation. So how does it react to that? This solar radiation might be very controversial to my feeling of privacy, or what I would want to look at, what I want to look at, so my view. So we're trying to deal with these conflicting parameters and bringing them together. And this is what we do when we talk about design, and this is what we do when we talk about variation in buildings. And yeah, being very fascinated by how HDB has actually developed in a very short time. I mean, it is very fascinating to look at a city like Singapore, that something like that could possibly have happened in 50 years. And it's very interesting that everything is built upon ownership here. So maybe this is one of the reasons why it's also so successful, because there's an identification with what you have. Still, I believe that there is a growing desire in the population as well for this variation as well, in order to meet more individual desires. So this would be one of my questions. I know it cannot be answered. It's a more conceptual question really that I'm still interested in.
Oh, thank you. But I think for HDB, we try our best to deliver quality and variations and options for the residents. But I think like earlier we have discussed this, affordability is always an issue, and so whatever that we come up with, we must always make sure that the cost factor is actually to be controlled. But the good thing about HDB is that because of the economies of scale, and once, let's say, if they roll out and there's enough size for it, the cost will come down. So that's why we find that we can work to our advantage also when we look at new areas. They may cost a little at first, but we have to see the long term on seeing that how actually we can press the price down. But I thought I want to follow up one question because I saw your last slide, which you showed HDB and you says the possibility of the changes. So my question is this: have you all considered? I mean, 3D printing now is the big word, but it's now the scale is actually very small. I'm very sure my colleagues from BCA is also asking the same question as me: is there possibility for 3D printing to reach scale like what we are doing for precast, such that you know that will really make the efficiency in producing in factory format? So do you think it's possible, and when can we see it? Next year?
Unfortunately, I cannot answer that. But yeah, 3D printing is something which is very interesting to us, of course, as well, but also for the reasons because we can very quickly produce different things. So also we have to think about what do we really use it for. And so this is referring back to what I said before. Now looking at 3D printing, it is very promising for loads of production industries. But of course, because of the scale, there are loads of loads of difficulties coming up for architecture, for building industries. Like I showed an example of concrete walls, and concrete is still the predominant material if we talk about structural systems, so load-bearing systems in a building. And yes, there are attempts currently going on researching and printing concrete, but you always have this difficulty that concrete is made up out of the concrete matrix and then the reinforcing component, which is out of steel. And since printing is layering very uniform material, powder material is building layer on layer, you can create wonderful geometries, but you cannot really engineer it that well. So you cannot really engineer the force flows that where you would need reinforcement for. So there are big difficulties, and what we are thinking about is still also on a conceptual level, how do we translate that to a large scale? So my question is always, is the brick, for example, the large scale application of what we have in powder in a small scale? I mean, I know it's not the end of, it's not the answer, but I'm always thinking about it. What does it look like? Well, what is the resolution that we're dealing with?
So the wait is still a little bit longer.
Yeah.
But anyway, I'm quite amazed with the tiling robot, and definitely want to talk to you more about it after this lecture. Anyway, maybe we move to Daniel.
Johnny, taking your question, what agency could do, for instance, for electric cars, electric vehicles, I think maybe it would be even good if nothing has to be done to have electric cars at all. So no diesel, no petrol, or not even electric cars. And actually, I see a very good development that with the HDB you try to have a community, everything for the community within a short walking distance, right? Food, medicine supply, shopping, and it's more and more concept. So there even cars are not needed anymore, which is very intelligent. I heard from the LTA plan that the walking distance towards the next MRT station shall be not more than 10 minutes. So probably that's acceptable somehow for the last or first mile. Even then a car would not be anymore needed. But let's say a lot of people still want to have individual mobility, road-based individual mobility. And if it shall be electric, which makes a lot of sense, from local emissions, so noise, NOx, emissions, or even global emissions, carbon dioxide emissions, to enable this technology more from, let's say, HB point of view, right now practically it's very difficult to charge. A colleague of mine had an electric scooter, and he had to take it upwards in the elevator to bring it up to his own flat to charge it there. because it was simply not possible to charge somewhere in the parking lot. I heard from Mercedes that they had 1 year delay to bring in the e-smarts because they could not find a place to put their charging stations. So if it can be implemented in the future planning, shall be condominiums, HDBs, to have dedicated places also for charging, this would be maybe solving this hen-egg problem. Like, okay, no cars, nobody's interested to put in infrastructure for charging, vice versa. Secondly, this is not only specific, we are not only looking about only electric cars, but only concepts of mobility. The second point is we're researching quite a lot on car sharing, where we see again a potential to reduce traffic and to reduce cars on the road. Even there, it would be very helpful to have, let's say, dedicated places for car sharing. There are a lot of initiatives right now. I know from BMW, also from other companies. And one still remaining question is where to leave the car. You don't want to bring the car A to B, and have to go back again to A. So very often you want to go to A to B and leave the car there, and someone else is taking the car. But that means you have to have a parking place. It's not only for HDB building, but in general a topic independent from electric cars that would be necessary to solve if this, which is also in the 5-year master plan of, or the master plan of LTA also highlighted, they want to focus more on car sharing again. This is something that has to be considered.
So I'd like to respond to that a little bit because I've been working with LTA on this charging issue for these electric vehicles. Okay, first we talk about car sharing. I think the thing about car sharing is that first of all, we are working with the vendors, but we understand that there must be a certain usage level before it becomes economically viable for this. So we did some tests over at Pongo, where we first set it up, and then we measure the success of this car sharing so that it becomes a viable business for the vendors, because this is very important. Then after which we propagate it in Pongo, and we tried like what is the distance away. That means how many car parks away that you actually have this car sharing scheme set up, and still you get enough customers to make it viable. So these are actually some of the things that we are doing. This for car sharing. Once we have ascertained this, then when we do our developments, we'll put in place that we'll work together with vendors, and they will come in very confidently, knowing that such facilities, they are able to make a business model out of it. Now, the electric vehicle, the thing is, the biggest challenge that we face is the chicken and egg problem. The thing is that we don't want to put a lot of electric vehicle charging lots, but if the take-up rate is by the residents and you don't have anyone who owns an electric vehicle, then that's a big problem, because ideally these lots have to be reserved for the electric vehicle for charging, because charging takes some time. I understand something like 8 hours, or maybe faster if technology improves. I guess you can verify that. But the thing is that if you don't have any electric vehicle, and the normal cars found that these lots are always empty and they are not allowed to park on it, that becomes a problem and a complaint case for us to deal with, you see what I mean? So it's a chicken and egg thing. So it's not entirely not solvable, but it's something that we need to study a little bit further. How can we come up with a solution that will still allow people to charge their vehicles easily, but will not invite such complaint situation where people feel that, hey, you know, this lot is not in use and I have to go all the way up in the parking to find a parking lot. And unfortunately, Singaporeans doesn't like to walk down the multi-story car park and they complain about it. But these are issues that we are actually working on. You want to say?
Just one last comment to car sharing. We have done a lot of studies, also user preferences studies. It's quite challenging to establish car sharing here. It was never successful so far. But one thing that is also very, from commercial point of view, very, it's a boundary condition. Taxis are comparably cheap. Car sharing works fantastically in Munich. It's really a success. They make money. That's because taxis are very expensive. So if you don't own a car and want to go quickly from A to B, car sharing is really the option, the mode of option. Here you take a taxi and it's still affordable. So yeah, for charging, you're right. If you use a normal household plug with 13 amperes, depending on the size of the battery, it takes 6-8 hours, right? And what we try to achieve, it needs 360 amperes. By the way, that's another issue we have discussed with Singapore Power Grid quite intensively. There's another challenge, but that's research. That's a good thing.
Anyway, thank you so much. Before I open up to the floor, do you have any last thing that you want to say before? Maybe we open up to the floor for questions, please. Maybe it's useful if you let us know.
Yes, I
who
think
you
it's
are.
on.
Yeah.
Afternoon, I'm John. Quite different starting point between HTV and the three academic institutions for obvious reasons. I think I want to take advantage of the three academicians on the panel today. I'm still grappling with the real relevance of your research to Singapore. I'm very selfish about that. So I know you have some, because short of the time, you have to go through it generally, but can the first one dwell a bit more on the application of your drones and all this monitoring to our major problem actually is a morning peak traffic problem. The second question to ETH is, I'm not sure how relevant is your research to Singapore. So it's for you to defend yourself. I mean, the tiling part, I can see that you can save a little bit of time within a very small amount of time in the overall construction period. So you're squeezing a little bit out of a small portion, so your ROI is very small. The other thing is that work can be organized quite easily with a large number of teams because they're all independently done, different from the structural work, which is dependent. Yeah? But the positive thing is I'm very curious about your student center in ETH. It's made of wood, is it? The whole structure is timber, it's not concrete. Can you maybe tell us a bit more about that design? Because it's a very fascinating column-free, right, structure, so to speak. The question to TUM, I'm not sure how you pronounce it in Germany. Let's call it TUM, is I'm very curious about your, I think if I'm not mistaken, you talk about a few kilowatts or 700 kilowatts between the use of the vehicle and the aircon part of it. You hit on the head of the nail in actually trying to reduce the consumption of energy on the aircon part. But I'm not so sure why you say all you need to do is cool the head. I think there's more to the visceral part of the body than the head that will make your exercise work. Thank you.
I suppose we can start in the same order as you asked the questions. So if I understand correctly, you were asking about the morning rush hour traffic. But that, of course, is not a problem unique to Singapore. Every major city has the same problem, even some cities that are not so major. I think what is perhaps unique about Singapore is its environment. It is basically an island city, so certain resources are very scarce, such as water, and also because of the particular topography of the way the hills are placed and so on, certain routes are not perhaps easy to draw. So I don't know if drones have any application to morning traffic. I think morning traffic is more of an issue of you know, better adaptive transportation. Now, if you can use drones for transportation, like, you know, imagine an autonomous helicopter picking you up from your home and dropping you off at work, I think that's a bit too futuristic, right? So yeah, please. Okay. Yeah, okay. So I think. Yeah. So you know, obviously, in the time I have here, I cannot go through all the details of how the mathematics work and so on. But at the Smart Center, we think that this is actually a feasible scenario. To give you an idea, at the moment there is something like that happening with Google Maps, right? If you get Google Maps to tell you how to go from here to there, it can suggest several ways and it can tell you how much traffic is in each path. If you can imagine an autonomous vehicle, and now I realize this is far into the future, right? Autonomous vehicles are not ready to be deployed. That can be done much more efficiently, because once you lock your Google Maps into a particular, a path, it is very difficult for the driver to change for reasons of safety, if nothing else. If the car is driving itself, then it can automatically adapt to the traffic conditions. And moreover, there's a concept in game theory that says that if you have multiple agents trying to achieve a certain goal and they're not cooperating, actually, when each one of them is trying to achieve that goal, it make the overall situation worse, right? So if all of us are trying to take a certain route because that's the least traffic route, well, guess what? Now it became the maximum traffic, right? So if the vehicles are automated and they are coordinating somehow with a higher level authority, so to speak. By authority, I mean a computer, basically, not a political authority. So you can imagine that this global optimization becomes better, because now this program, so to speak, will know what will happen if it reroutes everybody in a certain way. It can achieve a better, a better outcome. So this is sort of the grand idea. Now, of course, I realize this is very far from reality, and again, because autonomous vehicles are not generally accepted yet. There's no regulatory framework for what happens. There's issues of liability. There's issues, all kinds of issues. And if my colleague who specializes in that, Professor Frazzoli, if he were here, he would tell you that the highway is a good example where autonomous vehicles are more readily deployable. Because in the city, you have too many dangers. Kids running in the road, all these kinds of things. In the highway, it is much more controllable, right? So you could imagine a scenario where the moment you enter the on-ramp, you yield control of the vehicle to in automated fashion, and then you can answer your email and so on while your vehicle is driving, and then perhaps 5 or 10 minutes before the vehicle is about to exit, a loud alert comes up, okay, you're in control again, and as you go into the off-ramp, you drive again. This, at least my colleagues, they believe that this is much more feasible in a reasonable amount of time. And now Singapore is a very good place to do that, because the way the road network is structured, it is kind of a closed system, right? It's not like New York, where you get onto the highway and maybe your next exit is Boston. In Singapore, it's a very finite space. There's a lot of opportunities to install sensors and other control systems. So it is very, very well appropriate for the particular scenario here. Yeah.
And anyway, before going to the one, maybe I just say something.
Sure.
For me, anyway, without going to whether is it possible or not, autonomous vehicle, I thought that if you go for buses, that will help to solve a lot of our problems with bus drivers. if you imagine that these buses can actually just move by themselves to certain location, but of course, whether is it possible or not, that's another thing in which we will have to look into.
Yeah, obviously buses
raise productivity.
Yeah, buses is something that we're also thinking about, and also my colleagues mentioned the last mile or last kilometer problem. It may not be a problem for people who are young and can walk easily, so it's just a matter of laziness for them. It can be a very serious problem for elderly people or people who have disabilities, and they cannot quite make it so easily from the bus stop to their home. So then the availability of autonomous cars to bring them about is obviously very important.
Okay, thank you.
I would like to answer in a very similar fashion. First of all, there is no, or there are only little problems, a little number of problems really only constrained to Singapore. So most problems that we are dealing with apply globally and to Singapore. And maybe Singapore is, one thing that I also want to repeat, it's a scarcity of resources. So in 3 aspects, human labor is scarce, material is scarce, and space is scarce. So we believe that that's one thing that maybe did not come through before when I related to 3D printing technologies, that robots can be applied on this level, on this scale that we're dealing with. So when I talk about human resources, we believe working with these technologies that you can actually raise the skill level of the people who are dealing with. So you're not so dependent on low educated skills, but on rather higher skills. So this might be something very interesting for an environment like here, which is actually very much focusing on high technologies, and then trying to export them again, and like export them globally. The second question, or the second aspect, materials. I did talk about the resolution problem between 3D printing and robots. So to answer that a little bit more specifically, the wood construction roof, for example, is conceived out of very simple wood slabs, and they are all the same, just like the brick. The brick is always the same component, but the way you arrange it is very complex, and that's where the robot comes in very handy and efficiently. There are certain points where you could not even build it manually even more, where it's not only a matter of efficiency. So this is dealing with material resources, and if we talk about simple and cheap components, this is something which is again very relevant in a city which has its constrained resources. We could even take it as far as to talk about recycled materials. We are in our team, we're not yet dealing with it, but there are other teams researching in that within the FCL. And then the third question, of course, space. Also, space is very limited. So how do you operate in a limited space? And again, we believe that robots are applicable technology on a medium-term perspective, because they can operate in limited space. And by having the process at least partly automated, you can even think about building 24/7, something that is not possible by now because of the noise we create, because of dust we create. So if it's a machine activity, it can be much better controlled.
Okay, John, then I come to your two questions to me, to relevance for Singapore and the issue of cooling of the head. The question is very good because more or less NRF is funding us, and that's money from the people from Singapore. So what is the benefit back to either people or to the state of Singapore? And this question is always asked every time by our Singaporean scientific director, Professor Subodh from Arian. And Tomcreate and all is looking at a lot of a variety of topics where we see that Singapore in one day can play a role in electromobility. We pretty much sure that Singapore will not be able or will not have an OEM for a car manufacturer. This is probably too labor-based and too expensive. So agreeing this car might be not something that will be built here in Singapore. I don't know, maybe a good surprise. But why we did the car is actually to understand the whole system. As a university, coming from industry and going back also to industry, universities are coping with certain topics, research topics, and it's sometimes very far from actual reality. There are a lot of little details, but that makes it not 100% applicable for actually coming on the market. So building up a car was for us kind of a learning process, really from the whole system down to components to understand exactly the requirements. There are so many little things you would never accept, saying we develop a battery system. You would not know from the open domain, from the research domain, what are the requirements. You will never hear that from the OEMs because that's their advantage. So that's why a car. Second one is also kind of a light tower project to show actually the idea to become. Singapore is becoming a hub for development, for research, R&D in general. So that's why I think I understood Create is somehow also was established, and this car shall also show a little bit. Hey, if you want to, you can start a rocket from Singapore. Bring in people, bring them together, and yeah, everything is doable. So we also see ourselves a little bit with the vehicle project to a little bit show Singapore. In Singapore, you can do actually almost everything. if this is answering your question for this, the first question, I would come to the topic of cooling the head. So the overall approach is here to not look anymore on temperature, but on feeling, on comfortability. So it's more the topic of ergonomics. We have a chair of ergonomics in this topic, and from a lot of theory, that's again only theory, from topics, you can identify the most sensitive parts. It's not only temperature, it's convection, so wind, also direct contact to materials, so the heat transfer coefficient. But we have identified that mainly the head is one of the most sensitive parts on the body. And this one has to be mainly, let's say, well-feeling to be able to drive well, to be concentrated. And that's why we want to bring in the cooling as close as possible to the most sensitive part, and the head is the most sensitive part. A second or two more advantages we have with this approach is that we can switch off zones very easily. We have 4 air outlets on the roof, and we can switch off very easily zones, and with that we can again decrease energy consumption. And third one is, if you think about taxi usage, for instance, the wind will not blow the potentially existing germs from the front to the rear passengers. That's an advantage. The big disadvantage of this one is we have to have a very, very long path of the air ducts coming to the roof, which makes our B pillar, for instance, very wide. I know from some colleagues of BMW, they have tried it already several years ago, but they didn't continue because they thought it's too difficult. But the good thing is here is we are in research entity. We really have the freedom to look on feasibility, to prove concepts, and maybe not be 100% sure we have to bring it to the market, so, but at least showing the potential.
Actually, John asked a question that I also wanted to ask, is that did you all conduct behavioral studies to more or less ensure that that is actually the way to enhance the comfort level? Because, I mean, from a layman point of view, I felt that most ladies do not want their hair disturbed.
So your first question, or last comment, we don't target any hair dryer, so not a stream of air. It's more like a very, very low velocity, because high velocity of air would be, again, not at all. That's actually, we were never thinking about women in this sense of the, we should, right? But it was more about, again, comfortability. If you have a too high stream, like this one is very uncomfortable for me, to be honest. I'm sitting in a stream of the wind here. There is really also from research known exactly what temperatures, what humidity, this is a big factor by the way, and what kind of streams is important to still feel comfortable. So we have very wide air outlets where the air is more or less dripping down. Your question is about actually proving this. This is a PhD topic of one of my students. And, we are not so far to prove it in reality. So we have set up 2 test benches. One will be in a really in lab environment, and the second one will be in this vehicle. So the vehicle is not still finished, and also this lab-based test setup is also not finished. Actually, you should start first to do that and then implement this vehicle. I am aware of this. On the other hand, I had given a certain time frame until finishing this vehicle. This was 2.5 years. And we do it a little bit different way around. We propose certain technology, and we have to still prove the concept. You're absolutely right. We hope we can achieve something. From theory, with simulation, we have shown it is possible, but we still have to prove it in reality.
Thank you. Now, I mean, sharing from the housing point of view is that we also are studying about the thermal comfort that people feel within the living environment. So it's one thing about simulating and telling you that this wind speed and the humidity is satisfied. There's another thing that we also need to study, how the human actually receive this and perceive this. Yeah.
Sorry, don't want to talk about this, but there are some concepts already for buildings to have cooling plates, right? It's only convection, it's not wind anymore. This is, I think, also at Ariane, at NTU already established. It feels very good. If you imagine all the walls would be somehow cool and it's radiation, or some like convection but not wind, you feel much more comfortable. So it's something we also have a little bit stolen the ideas from housing technology.
Anyway, maybe I open to the floor again because time is also quite tight. Is there any questions? Yes, please.
Excuse me, I just wonder, I look at this whole thing quite differently from all of you. I want to get your view on biomimecy. Because the first speaker is talking about the energies of humans and so forth. But have we looked at the whole city just like a human? Inside a human body, you have complex, a lot of movement, unpredictable, and all the others. And also very robust. Robust in the sense that you go from different states of their health and so forth, different ages and so forth. So I just wonder, have you all borrowed ideas from there? There's enough sensor, and there's also self-repair mechanism and so forth. And there are traffic control of different type. Earlier on we talked about buses, cab, and all the others, but I just wonder, I want to get your view on that, because being an academic, have you sort of borrowed the idea rather than take a hardcore engineering approach, try to solve it, but actually the human body is just one of those, or even you take animals and all the others. Thank you.
I think this is going to me, yes. So, this is a very good question, and I think when it comes to biomimetics, very often it provides you with good analogies and inspiration, but like every analogy, there is only so far that you can take it, right? You know, you cannot obviously. My favorite example is that airplanes that try to emulate birds, but they operate differently. You know, they are similar in the sense that birds have wings and airplanes have wings, but birds fly by flapping their wings, airplanes use, jet engines. And there is very good reasons for that, because nature and human engineering, they optimize different metrics, right? So I think it's a very similar thing with the city. You know, you cannot really compare, because we sense different things, we have different goals, that evolutionarily humans developed in order to survive, beat, the predators, procreate, and so on. The city does not have similar, similar optimization metrics, and moreover, the technologies available to the city were not available to evolution to creating a human, One analogy that I would like to pursue perhaps a little bit further is the analogy of awareness that I mentioned earlier. Because in every case, when you have a computational problem, it is not so easy to say, well, I'll buy a bigger computer and I'll throw it to a bigger computer. Even that has its limit, right? You know, how much computation you can have. So then it becomes very important when you have, this is another name for it is the deluge of data. If you have a deluge of sensory data that is coming to you from different sensors, in a human, you know how many sensors we have, fingers, you must have a way to prioritize how much of this data is most relevant for your survival at any given moment. So some of this data, it can be used in the background, or maybe not used at all. You just throw it away. Some of this data is very crucial. In the context of a city, if you have a security camera and you observe someone acting funny in a subway station, obviously you want to pay very close attention, right? Because maybe you have a potential terrorist threat. Or if you are in a public event and someone is having a heart attack, you want to concentrate on that and spend more resources to deal with the situation. And again, the way the human brain does it is obviously not the way you might do it in a city, but you use it as inspiration, and then you try to bring the toolset of engineering, computation, mathematics, and so on in order to solve the problem. But the solution you arrive is going to be very different, obviously, than the way nature is doing it.
For a human body, immune system is one of those. Your repair mechanism you talked about just now, suicide and so forth, self-repair and all the others. They are all localized factor, distributed, not necessarily everything due through the brain. So that is why I would urge that perhaps rather than dismiss the whole thing, borrow some of the idea.
Oh yes, we are. I mean, I think
rather because the type of sensor built in could be relatively simple and so forth. Okay. So I'm just thinking sometimes we tend to borrow too much. I'm not running down the whole engineering, don't get me wrong on that, okay? But I thought that there is a lot more. It's a lot more robust than we would think. Because think of all the different piping systems that within the body. And that's very much like a city. And also all the movement. Thank you.
I don't think we disagree, actually. I agree with you.
Maybe it's take it as a suggestion to study further on this.
Certainly.
I think because of the time, maybe we just open up for one last question, a burning question. Okay, please.
Raymond Kwok from Oxford Economic EPC.com. This question maybe you can share with the panel and Johnny. I like one of your last slide, I think one or two before that. You're talking about different layers of things that you're looking at. Voice was the last one, and then you say you're going to look at complex system to integrate all the way. I think that slide is extremely interesting because in the sense that, you know, I've listened to a lot of talks, but a lot of people ignore the voice architect. Basically, we look at, you know, ratio and all that, but the voice level, maybe you can share with us how would city in the future manage the voice, you know, acceptabilities or livabilities.
Talk about noise, is it?
Noise.
Okay, I think maybe I approach it this way. As cities get denser and people begin to live closer to each other, noise would definitely become an issue. And of course, with advancement in technology, like now we have cars and all this sort of thing, they're coming nearer to the people, to the living spaces of people. So this is one area which, not just Singapore, I think many cities are facing this problem. I was just in Hong Kong. In fact, I would dare say that in Hong Kong, they are a little bit more advanced in this area than, well, for me anyway, in HDB, and we're learning from them. They begin to realize that noise is a big issue, and for any of the developments, they need to simulate what is the noise impact into the living spaces of these residents, and how can they actually mitigate it, at least to reduce it. Because long-term issue, this can cause health problems also. Okay, so I do not have all the answers because this is something that we are also learning. But one of the challenges that we face is that for Singapore, we are in a very tropical setting. So HDB in our most ideal situation, what we try to push for is what we call as passive design, where we try to reduce energy by not encouraging people to go for air conditioning. So if we do that, then you see there's this compromise because you want them to have natural ventilation, full opening, and if the roads comes nearer, noise is going to impact them. So how are we going to balance this too? Now that's a big challenge. Also, well, I'm talking about Hong Kong because I just went to Hong Kong, I just talked to them. They have actually did a lot of studies in this area where they came up with windows that actually still allows natural ventilation, but block off substantial noise. So we would like to study this. Of course, many other people also came up with other solutions like having balconies and that sort of thing, but on the cost and the reduction, it doesn't make sense at all, honestly. We have done some studies. So that's why so what we're thinking is that first, let's get the science correct. How does this actually noise impact the living spaces first? Then we see it, what mitigation measures can we actually look into addressing them? So that's how HDB is approaching the problem on the thing. But I don't have all the answers if you want the solutions on this sort of thing. But once we have it, definitely we'll share on the thing. Okay? I think you can see substantially along there I put in progress for the noise. But is this something that we're studying? Please.
I would also like to answer very quickly from our perspective to that, because we are trying to deal with complex systems a lot, like what we perceive as complex systems. So all these environmental factors that influence facades, I mentioned it before, and how they contradict each other or where they merge. As I said, solar radiation, noise is also one, or then again the view out of your apartment. This is where it becomes interesting to use these computer simulation systems in order to come up with like meaningful solutions. So this is where I'm saying that where a facade would all of a sudden not look like it looks today in a very orthogonal and repetitive pattern, but it would react differently to where there is more noise, it would be more closed, and where there's less noise, I can enjoy more of the view, I can open the facade more. So this is why we're interested in variation. And another aspect which is interesting about that topic in particular, like like from our point of view, from the planning perspective, dealing with noise and is still quite difficult. It's quite hard to simulate. Noise and light are actually both still measured in physical models. So those who are dealing seriously with that still build like scaled models in order to measure that. And that's just something which is then conceptually very interesting to us, because we are often asked, well, I mean, what does it mean to build models with students? They are 1 to 50 scaled. They are 2 meters high. And this is just, there are a few of the implications why it still makes sense to build models, physical models, and to abstract a certain reality by doing that. So.
Thank you. I think this is very interesting, and I think we can have this conversation even after this discussion. But in the interest of time, I would like to thank the 3 speakers for the interesting discussion and your presentation too. So if you will be with me to just give maybe thank you to thank the speakers.
Thank you, and now we would like to invite Dr. Lee Min Hee, Acting Director of CLC, to present the panelists with a token of appreciation. Dr. Hee, please. Ladies and gentlemen, we have come to the end of our lecture. We thank you for your participation today. Do look out for our next lecture on our website, www.clc.gov.sg.